Okay, here we go again. This is the second video in the Abstract Algebra series, where we'll discuss modular, arithmetic, and binary operations. This will kind of wrap up the prerequisite material and get us in a good spot to discuss groups in the third video. And then for many videos after that, we will discuss groups. There's a lot to say about them. Okay. Now, the pacing of the videos will slow down somewhat after the next video or two. I only had prepared a few videos in advance. So let's get started. Yeah, so first off, we will mention Cartesian products and equivalence relations. Then we will discuss modular arithmetic, and then we'll finish off by discussing binary operations. So, definition 9. Remember, we're going to do running definitions and examples and theorems. So if you're following along, it should make it easier in your notes to keep up. So definition 9, let S and T be some sets, and we form a new set from them, denoted S cross T, and this set consists of all the ordered pairs where the first entry comes from S and the second entry comes from T. Again, these pairs are ordered, so in general, AB does not equal BA here. So, and S cross T does not equal T cross S unless S equals T. For a quick example, suppose we have A is the set containing 1, 2, 3, and B is the set containing 4 and 5. You can enumerate the elements of the set A cross B pretty easily. I've done so here. So we have 1, 4, 1, 5, 2, 4, 2, 5, 3, 4, and 3, 5. We don't seem to be missing anything there. And in general, say A is like a finite set with n elements. We write this like absolute value sort of thing. We use this notation to denote how many elements are in the set A. So say A is a set with n elements and B is a set with m elements where both of these are finite. Well, then A cross B has m times n elements. And we can kind of see this up here, right? So A has 3 elements and B has 2 elements. And then A cross B has 2 times 3 is 6 elements. Definition 10, by a relation R on a set S, we just mean a subset of S cross S. And we write X, R, Y sometimes if the ordered pair X, Y belongs to R. So let's do a fun little example. Consider the set S containing the elements 1 and 2. Let's actually count how many relations there are on S. So first off, let's, a relation is just any subset of S cross S. So let's describe S cross S first. That seems like the first step. S has 2 elements, so S cross S should have 2 times 2 is 4 elements, and indeed, we've enumerated them here. Okay, so we need to find every subset of this set with 4 elements. Each ordered pair is 1 element, of course. And it might sound silly, but the empty set is a subset of every set. So we do always get one relation with 0 elements. And similarly, we could just say that S cross S is a relation on S. So we have one relation with 4 elements, the whole thing here, and we have one relation with 0 elements, which is the empty set. And now, how many other subsets can we get? Well, how many subsets can we form that contain one element? Well, I can see 4 ways we could form that, a subset with one element. What about 2 elements? Well, so we have 4 elements and we need to pick 2. And you can go through this in detail if you really want to, but there's a combinatorial way to do this. So 4 choose 2 is how we denote the number of ways to choose 2 elements from 4. And that comes out to 4 factorial over 2 factorial times 2 factorial. And that comes out to 6 relations with 2 elements. And what about how many relations involve 3 elements? Well, one way you can think of this, you could do this combinatorial binomial coefficient thing we did here and you get 4. Or you can say, well, if we're taking 3 of 4 elements, that's the same as leaving out 1 element. So we pick 1 element to leave out and we get 4 ways to do such. And this gives a total of 16 relations on S. If you're, I did this kind of quickly and using like a fun combinatorics little trick, but if you are not really sure about all of this, it might be a good idea to check this manually. You can write out all 16 relations here. Okay. So I know it feels like we're vomiting out definitions very quickly, but there's a lot of this stuff and we need to get through it. So 11, let R be a relation on S. We say that R is an equivalence relation on S if R satisfies the 3 criteria: reflexivity, symmetry, and transitivity. And by reflexivity, we mean that each element in S is related to itself under R. By symmetry, we mean that X is related to Y implies that Y is related to X for every X and Y. And then by transitivity, we mean that if X is related to Y and Y is related to Z, then X is related to Z for every X, Y, and Z. And lastly, if in fact R is an equivalence relation on S, we sometimes use this little tilde to denote that X and Y are related. This in LaTeX, this is the \sim sim in math mode. And these might seem like kind of weird. And the way to think about this definition, it is a good definition to memorize because you use it so much everywhere in math, but an equivalence relation is a relation that behaves like equality. So, for instance, every set is equal to itself. If a set A is equal to a set B, well, that means B is equal to A as a set. And if set A is equal to set B and set B is equal to set C, well, then set A should be equal to set C as well. However, it's like you can't just assume a relation is an equivalence relation. Great care needs to be taken. Now, for instance, the inclusion relation or the belonging relation is not an equivalence relation. So like 0, the number, belongs to the set of all integers, and the set of all integers belongs to the power set of all integers, but 0 does not belong to the power set of all integers. The set containing 0 does, though. So some care needs to be taken. Similarly, subset is not an equivalence relation. Every set is a subset of itself, but just because I'm a subset of another set doesn't mean that set's a subset of me. It's like all dimes are coins, but not all coins are dimes. Okay. So again, let's consider this set S is the set containing elements 1 and 2. And let's work out which of these relations are equivalence relations on S. You might want to pause and just kind of think through this for a second. I'll give you a second. Okay, so the empty set is an equivalence relation, like vacuously. It seems kind of weird that we are insistent to include it, but it's important to include it for logical reasons. S cross S is an equivalence relation as well, and this always holds, not just for our specific example. So any S cross S is always an equivalence relation on S, not just in our example. The third one, 1, 1, and 1, 2, the set containing those is not an equivalence relation. For instance, we don't have reflexivity, since 2, 2 doesn't belong to this set. And we also don't have symmetry, because 1, 2 is here, but 2, 1 isn't here. Finally, the set 1, 1 is not an equivalence relation, or the set containing 1, 1 is not an equivalence relation, because 2, 2 isn't present, so we don't even have reflexivity. Okay. I guess we didn't include an example here where transitivity fails, but you can probably come up with examples of that, and in fact, you definitely should consider doing so, because all three of those parts of the definition are really important. Okay. Let's talk about equivalence classes. And these are one of the reasons why equivalence relations are so nice. So definition 12, let tilde be an equivalence relation on a set S. For each x belonging to S, the equivalence class containing x is just the set x bar containing all the elements y in S that are related to x under the equivalence relation. And we denote this set of all equivalence classes by S, kind of looks like a divided by tilde. And that might be a weird thing, and we think of this as we're quotienting out elements of S. So it's important to note that the elements of the set of all equivalence classes, they're not elements of the set S, they're subsets of S. So it's like we're kind of reducing the set S to these subsets that in some sense we will see represent the structure of this equivalence relation acting on S. So let's make some observations. Equivalence relations are reflexive, right? So x belongs to x bar for every x. Okay, so that's good. So every x belongs to at least one equivalence class. And it turns out each x belongs to exactly one equivalence class. So if y belongs to x bar, well, then symmetry says that x is related to y. So x belongs to y bar. And you can repeat this for every element to see that x bar equals y bar. So every element of S belongs to precisely one equivalence class. And we summarize this by saying that the equivalence classes form a partition of S. And this is a very important concept. Okay. So given an equivalence relation tilde on S, let A be an equivalence class. So we call each x belonging to a representative of the equivalence class A. So again, since the equivalence class is partition S, each element of S represents exactly one equivalence class. And like we mentioned earlier, sometimes we can use equivalence classes to, in some sense, collapse a set from the perspective of a relation. And we're going to apply this concept now as we return to our study of z from the first video. Okay, so let's talk about this relation called the congruence relation. So definition 14, let x and y be integers, and let m be a non-zero integer. So if x and y differ by a multiple of m, that is, if m divides x minus y, we say that x is congruent to y modulo m, and we write x triple bar equals y mod m. Usually writing the triple bar feels a bit excessive though, so we form a slight abuse of notation and write x equals y mod m. X equals y mod m. I need to enunciate. Okay. So just for a quick example, does 2 equal 3 mod 5? The answer is no. So 2 minus 3 is minus 1, and 5 definitely doesn't divide minus 1. What about does 12 equal 10 mod 2? And we can try the same thing. So 12 minus 10 is 2, and well, 2 does divide itself. So 12 equals 10 mod 2. I'm going to state this as a fact. We're not going to prove it, but it should be intuitive after a while. So for a fixed non-zero integer m, equality modulo m is an equivalence relation. Under equality modulo m, x bar is the set of all integers y, such that y equals x mod m for each integer x. And we call x bar the congruence class of x modulo m. Again, I'm not going to prove this, but I think you should be able to reason through this, maybe with some specific examples once we've done a couple of those, and convince yourself that this is true. And now you might say, well, what's the point of all of this? Why are we talking about this? So let's think about what can we say about the structure of z under this congruence equivalence relation. So another definition. I promise they do end. Let's fix some m. It should be non-zero. Integer m that's not 0. I apologize for the typo. The integer is mod m, denoted z mod mz, or z slash mz, but we read it integers mod m, or z mod mz. Z mod m, wow, is the collection of congruence classes of integers modulo m. So for each a belonging to z mod m, a representative of a is an ordinary integer x with x bar equals a. So if we're being really informal, we might just drop the bar and write x instead of x bar if there's not any risk of confusion. However, this is, again, like an abusive notation. So if you're studying for a course, keep that in mind. Your professor might hiss at you. So we've talked about this a little bit, but we haven't really done an example. So let's change that. Let's figure out what the congruence classes are in z mod 2 and z mod 3. And our strategy here is that we know a priori that the congruence classes form a partition of z. So we should be able to limit our computation somehow. Right? We should be able to maybe just determine the congruence classes of some element and see where we can go from there. So let's just determine what the congruence class of 0 looks like in z mod 2. So let's see what would it mean for y to belong to 0 bar. Well, clearly 2 divides y minus 0, if and only if 2 divides y. So, but that just means that y is an even integer. So 0 bar is the set of even integers, as we have here. Okay, so that's pretty good. We've already gotten rid of half the integers. And let's now try an element that doesn't belong to 0 bar. 1 seems like a good choice. Well, so clearly 2 divides y minus 1 precisely when y is odd. Another typo, that should say is. I'm so sorry. So 1 bar is just the set of odd integers in z mod 2z, in z mod 2. So we've broken the integers into two congruence classes under Congruence mod 2. And it's one contains all the even integers and the other contains all of the odd integers. Now, in particular, we've written it like 0. We've written these 0 and 1 as like some distinguished representatives, but nothing is stopping us from calling this congruence class, say, like 4 bar. So 0 bar equals 2 bar equals 4 bar, etc. equals minus 6 bar, for instance. Yeah, so this accounts for every integer. So we have this as a summary. And we can use a similar technique. Just try a couple of elements in Z and see where they take you to see that Z mod 3 is just 0 bar, 1 bar, and 2 bar for these 3 choices. And we notice a pattern, right? So maybe it wasn't clear just from this first case, but here we're like clearly counting by 2 in each class. And similarly here, and here we're counting by 3 in each class. And in fact, this pattern holds in general. So let's make a few other observations. One important thing is to note that, the conjugacy classes depend on M itself. So 0 in Z mod 2, or 0 bar in Z mod 2 is not the same set as 0 bar in Z mod 3. We can see this here just by comparing them. So 2 belongs to this one, it doesn't belong to this one. 3 belongs to this one, it doesn't belong to that one. So we need to be careful to specify M when we're talking about these. And again, yeah, we could have chosen a different representative for each conjugacy class. For instance, in like Z mod 2, minus 4 bar, minus 2 bar, 0 bar, all of these are the same, and so on. And like, again, this counting by like M, this pattern does hold in general as a way to compute equivalence classes in Z mod M. Namely, N bar is the set containing M, the set containing N, plus or minus any M. So each of these is an infinite class, an infinite set, of course. You should be able to convince yourself that this is true just based on like how we defined congruence, right? So there's this x and y differ by a multiple of m, so we should be counting by m in some sense. And that's exactly what we do. And with this in mind, we actually have that Z mod M always contains exactly M conjugacy classes, and we can enumerate them: 0 bar, 1 bar, 2 bar, all the way up to M minus 1 bar. And all of these are distinct, and they form a partition of the integers. So that's pretty cool and pretty intuitive. So yeah, congruencies are nice because they behave a lot like equalities, which is why we have the name equivalence relation, actually. They have some other nice properties, though. In particular, they play really nicely with respect to addition and multiplication. So I know we went, what was it, almost over 25 minutes without proving anything. That ends now. So we have this lemma. So fix some non-zero m as our modulus. If x equals x prime mod m and y equals y prime mod m, then these things hold. X plus y equals x prime plus y prime mod m, and xy equals x prime y prime mod m. So before we prove this lemma is basically telling us that we can compute in terms of representatives of each congruence class and not run into any issues. So this is like a well-defined, well-behaved thing, which is really nice. So let's prove this. So say x equals x prime mod m. Well, that means there's some integer k such that mk equals the difference x prime minus x. If y equals y prime mod m, then there exists an integer L, I like the LaTeX script L, with ml equals y prime minus y. So now let's actually compute. So x prime plus y prime, well, solving from here, x prime equals x plus mk, y prime equals y plus ml. So we substitute here, and then we rearrange, and we see that x prime plus y prime equals x plus y in parentheses plus m times, in parentheses, k plus l. And this is exactly what we needed to show to see that x plus y equals x prime plus y prime mod m. And we can do a similar thing for multiplication. It's slightly messier, but again, it's like a 1-2 line thing. You can go through it in detail if you want to convince yourself it's not a bad idea. And we again get that x prime y prime equals xy mod m. I guess I read the opposite, but it's an equivalence relation, so we're all good. X prime, or xy equals x prime y prime mod m. Very good. Okay. Now we've proven that this addition and multiplication of conjugacy classes is like a well-defined thing now, and like we can do it without worry. But in fact, it actually goes a little deeper because congruence actually inherits a lot of the structure from regular integer arithmetic. For instance, we have this distributive law. We have the associative property, which is to say we can rearrange the parentheses in any way that we like for both addition and multiplication. We have a multiplicative identity 1, which is just the class 1 bar. And we have an additive identity. Which is a 0 element. And this holds for every non-zero m and for all integers x, y, and z. Now, let's at least mention multiplicative inverses. So until now, we've actually been limiting our discussion to the natural numbers and the integers. So by a multiplicative inverse to a number x, we just mean another number x to the minus 1, read x inverse, such that x times x to the minus 1 equals 1. And in z, the only numbers with multiplicative inverses are minus 1 and 1. Both of these are their own inverse. But for example, 2 doesn't have a multiplicative inverse unless we expand to the set of rational numbers. And this is the set q equals the set of all fractions m over n, such that m is an integer and n is a natural number. Remember that I chose n equals the set containing 1, 2, 3, 4, 5. This is actually why I prefer that. I think it's a little slicker than having to specify that the denominator is non-zero. It's kind of baked in, so I like that. But we could also talk about multiplicative inverses mod m. So say we just are given some non-zero integer m, can we tell, like, what would it mean for an integer to have a multiplicative inverse mod m? So, well, here's what it means. So a multiplicative inverse mod m to an integer a is just an integer b with ab equals 1 mod m. And we don't know a priori if such a b exists. For instance, though, 2 has a multiplicative inverse of 3 mod 5, since 2 times 3 equals 6, which is just 1 mod 5. We do reduction mod 5 to see that. And here's a useful lemma that I'm just going to state and not prove because I don't want this video to be super long. But let's fix some non-zero integer m, and then an integer a has multiplicative inverse mod m if and only if a and m are coprime, or if GCD of a and m is 1. We'll actually use this a bit, so I will bring it up again at some point in a future video. Okay, let's conclude this video by briefly talking about binary operations. Let S be some set. A function from S cross S to S. Remember, S cross S denotes the set of all ordered pairs where each coordinate is from S. This is called a function S cross S to S is called a binary operation on S, or a law of composition of S into itself. If X and Y belong to S, we use the notation XY maps to, is how we read this symbol here, this arrow, maps to XY. And we think of this as like a product of X and Y. Alternatively, we might write this ordered pair as mapping to X plus Y, but this is typically only done when the binary operation is commutative, like if X plus Y equals Y plus X for all X and Y in S. And maybe just some quick examples. So addition, let's figure out which of these are and are not binary operations. So addition on Z, the set of integers. So what this does, plus maps A comma B to A plus B. And this is a binary operation on Z. But let's consider some things that maybe aren't binary operations. What about negation? So negation, it takes one input, A, and maps it to minus A. The problem is this isn't binary. So it's not a binary operation, right? There's no second argument here. Okay, for another example, let's consider division on Z. So this map sends A comma B to A divided by B. And no, the problem is this is not a binary operation because it doesn't map integers to integers. So for example, if we wanted to ask what do we get when we divide 3 and 5, you don't get an integer. So we need to be careful, you see. If we were to replace Z here with the set of non-zero rational numbers, then it would be okay. And we would get a binary operation. Or the set of non-zero real or complex numbers. Here's a different looking one. So I know we've talked a lot about numbers. What about multiplication of polynomials with real coefficients? This turns out to be, if you multiply two polynomials together, you get another polynomial. And if you multiply two real numbers together, you indeed get another real number. So that works. What about addition of congruence classes in Z mod n? And the answer is yes. If you add two congruence classes, you get another congruence class. Okay, so some various examples. And binary operations, like ice cream, come in various flavors. So there are traits that a binary operation may or may not possess. And let's consider these, or at least list them off in brief. Let S be some set with a binary operation. If x times y comma z, or if x times in parentheses yz equals in parentheses xy times in parentheses z, for every x, y, and z, we call the binary operation associative. So basically this is independent of bracketing. If xy equals yx for all x and y, we call the binary operation commutative. An element E in S for which xe equals ex equals x for all x is called a unit element in S. Now, if there's a unit element, we often just denote it as 1. It's conventional to do so. We might also denote it as 0 if we were using that additive notation mentioned earlier. So for example, this all comes from our discussion of the integers where x plus 0 equals 0 plus x equals x, and x times 1 equals 1 times x equals x for all x. And maybe as an exercise, if you're shaky on this stuff, you could go back over binary operations 1, 4, and 5 and determine whether they're associative, commutative, and if they have a unit element, and what it would be if there is one. So that'll conclude this video. Next time we're going to talk about groups, and things will slow down a little bit because, you know, these first two videos were mostly prerequisite material that I assume is a refresher for most viewers. Okay. Some of the material in this book, in this lecture, was also sourced from a book by Lang, and this is like the Bible of algebra. So if you want, actually don't read it, it's a terrible book, but read it later, but not now. Okay, thank you.